So we are going to look into derivatives of non-natural bases. This would include both exponential as well as logarithmic functions. So if we recall the natural base is E, and we know that E is approximately equal to 2.7182. But we could have other bases, such as 10, 2, and so forth. So all of those, any number other than E would be a non-natural base. So, for instance, if I have to define an exponential function, 2 raised x, 10 raised x, 4 raised x, 11 raised x are all exponential functions. With non-natural bases. In a similar manner, we could define logarithmic functions for non-natural bases. For instance, log base 2 of x, log base 10 of x, log base 4 of x, log base 11 of x, and so forth. They're all logarithmic functions with non-natural bases. A nice thing to note here is we could write any non-natural base in terms of the natural base. For example, log base 2 of x is simply the natural log of x divided by the natural log of 2. Log base 4 of x is natural logarithm of x divided by natural logarithm of 4. Log base 11 of x would be natural logarithm of x divided by natural logarithm of 11, and so forth, which is a nice thing to have. And also, in practice, if we have ln of x, then log base e of x refers to ln of x. Likewise, if we have log of x, then it refers to log base 10 of x. So anytime we have a log base 10, we simply refer to it as log. Anytime we have log base e, we refer to as ln of x. Now, how do things change with respect to derivatives? So we know the derivative of e raised x is e raised x. The derivative of any base other than e is simply a raised x multiplied by ln of a, where a is a non-natural base. Now you may wonder why this works. Let's consider derivative of a raised x, which is that, and let's just assume a to be equal to e. Then if I plug in e for a, I'll just get e raised x, ln of e. But we know ln and e are inverses of each other, and it'll just get cancelled, and we'd end up getting e raised x. And that is exactly the same result we've had in the past. In a similar manner, we know the derivative of ln of x is 1 over x. So if we consider a non-natural base, the derivative of logarithm base a of x would simply be 1 over x multiplied by ln of a, where a is a non-natural base. Why does this work? Again, if we assume a to be equal to e, the derivative of log base a of x would simply be 1 over x times ln of a, but I've assumed a to be e, so I have x times ln of e. Those two would go away, and we definitely revert back to the standard derivative that we have for derivative of ln of x, which is 1 over x. Here we have to find the derivative of 3 raised x. The base a here is 3. So the derivative dy over dx is simply 3 raised x multiplied by ln of 3. And that is the answer. We have 4 raised to x minus 3. So the base here is 4. But we've got to be careful because the power is not just x, rather it is 2x minus 3, which would indicate that we'd have to use the chain rule. So what is h prime of x? We are going to treat the power as x for just a minute. So the derivative would be 4 raised to x minus 3. But don't forget the ln of 4 because we have a different base. But then we've got to realize that the derivative of 2x minus 3 is 2. So the answer is 4 raised to x minus 3 multiplied by 2 times ln of 4. But we can use the power rule of logarithms and write it as ln of 16 because it states that we can move the power to the part inside the logarithm, so ln of 4 squared. So the answer would be 4 raised to x minus 3 multiplied by ln of 16. So here we have to find the logarithm base 10 of x squared plus 6x. So what we have inside is not just x, rather it is x squared plus 6x, which would imply that we'd have to use the chain rule. So y prime would be, we're going to treat x squared plus 6x as just x for the time being. So we have 1 over x squared plus 6x. But since we have a base 10, we have to multiply by ln of 10. Then we use chain rule. to take the derivative of x squared plus 6x, which is simply 2x plus 6. So the answer would be 2x plus 6 divided by x squared plus 6x multiplied by ln of 10. We may leave it as is, or we can pull the common 2 out in the numerator and we will have x plus 3 divided by, we have an x in common, so if we pull that out we have x times x plus 6 times ln of 10. Both of them are acceptable answers. So a similar process here, only this time the base is 6, and we are going to treat whatever that is inside as x for the time being. So we would have 1 divided by 2x cubed minus 5x squared. Since the base is 6, we're going to multiply by ln of 6. We've got to use chain rule because we don't have log base 6 of x, we rather have log base 6 of 2x cubed minus 5x squared, which would mean I would have 6x squared minus 10x. We can simplify quite a bit here, so 6x squared minus 10x divided by 2x cubed minus 5x squared multiplied by ln of 6. We have a 2x in common in the numerator, so if I pull 2x out, I would leave behind 3x minus 5 divided by, I have an x squared in common, so if I pull x squared out, I would have 2x minus 5 multiplied by ln of 6. I could certainly cancel an x there, which would give me 2 times 3x minus 5 divided by 2x minus 5 multiplied by ln of 6. So here is a problem where we want to find the derivative using a bunch of rules. One, the chain rule, then the product rule, because we have the product of two functions, x and 3 raised x plus 1. So I'm going to set u to be x and v as 3 raised x plus 1. U prime would be 1. V prime, since the base is 3, we would have 3 raised x plus 1 multiplied by ln of 3. And we have to take the derivative of x plus 1, which is simply 1. So, and that part is simply chain rule. So product rule states that y prime is u v prime plus v u prime. U is x. V prime is 3 raised x plus 1 multiplied by ln of 3 plus v is 3 raised x plus 1 multiplied by 1. So we have 3 raised x plus 1 in common. So if I pull that 3 raised x plus 1 out, I would leave behind x ln of 3 plus 1. You may leave the answer as is, or you could use the power rule of logarithms and move the x inside over there. So we would have 3 raised x plus 1 multiplied by ln of 3 raised x plus 1. So rewriting the answer, it's merely a matter of choice. If you want to, you can rewrite it, or else you can leave it as is. So here we want to find the derivative implicitly. And as we all know, when we find the derivative implicitly, there is a possibility the answer would depend on y itself. In most cases, it certainly does. So how do we go about finding the derivative? So we take the derivative on both sides. The derivative of 30 is simply 0. The derivative of 5x with respect to x is simply 5. Now we have to take the derivative of ln of xy. Now, this is where the properties of logarithms come into play. If you want to take the derivative directly, then we have to use product rule and then overcomplicate things. But if we realize the product rule of derivatives, logarithms, we know ln of x times y is simply ln of x plus ln of y. So I could take the derivative of ln of x times y as the derivative of ln of x plus ln of y, which is the derivative of ln of x plus the derivative of ln of y. The derivative of ln of x is simply 1 over x. The derivative of ln of y is 1 over y, but since y is a function of x, we've got to multiply it by dy over dx. So here we have the derivative of ln of xy. So I'm going to replace it in my equation. So the first part is the derivative of ln of xy. So I'm going to replace that by 1 over x plus 1 over y dy over dx. And then we have 5. Now I could move the 5 and the 1 over x to the other side. So 1 over y dy dx would be equal to negative 5 negative 1x, or 1 over x. I could combine the negative 5 and negative 1 over x and write it as negative 5x over x minus 1 over x. Since we have a common denominator, we have negative 5x negative 1 divided by x. We have a negative in common, so 1 over y dy over dx would be negative multiplied by 5x plus 1 over x, multiplied by y on both sides. We would end up having dy over dx is equal to negative y times 5x plus 1 divided by x. And as I mentioned, when we do implicit differentiation, that 99.9% of the time, the answer will depend on, the derivative would depend on y itself. So here is a problem where we want to find the derivative of the second derivative, to be precise. And oftentimes people would make this problem complicated if they don't use the properties of logarithms. And anytime we deal with logarithms, it is very important that we make use of the properties of logarithms. So f of x would be equal to x ln of x raised 1/2. Square root of x means x raised 1/2 plus 2x. Now, if I use the power rule of logarithms, the 1/2 that's in the power is going to move to the front. So x over 2 ln of x plus 2x. Which, if I take a common denominator, I would have x times ln of x over 2 plus 4x over 2, which should be x times ln of x plus 4x divided by 2. So f of x can now be written as we have an x in common, we have a 2 in common, 2 in the denominator. So I could write it as x over 2 multiplied by ln of x plus 4. So what looked like a complicated function now became quite simple in the sense that I have u and I have v. So u is x over 2, v is ln of x plus 4, u prime is 1 over 2, and v prime is 1 over x plus the derivative of 4 is just 0. So the first derivative is u v prime plus v u prime. U is x over 2, v prime is 1 over x, plus v is ln of x plus 4, and u prime is 1 over 2. The x's will get cancelled, which would give us 1/2 plus 1/2 times ln of x plus 4. Since we have 1/2 in common, we can pull that out and we'll have 1 plus ln of x plus 4, which would reduce to 1/2 multiplied by ln of x plus 5. Now we want to find the second derivative. The second derivative is 1/2. The derivative of ln of x is simply 1 over x. So the second derivative is simply 1 over 2x. Mind you, this problem would have been very difficult had you not realized that ln square root of x can be written like so, and it can be simplified and written in that manner. So it is very, very important to know the derivatives of logarithms and the properties of logarithms when we deal with finding derivatives of logarithms in general. So here is an application problem. So the temperature T in Fahrenheit at which water boils at a selected pressure P can be modelled by that expression. We want to find the rate of change of the temperature when the pressure is 60 pounds per square inch. So first off, we want to find the derivative of T. That is going to give us the rate of change in temperature. So dt over dp would be the rate of change of the temperature derivative of 87.97 is 0. Derivative of ln of p with respect to p is 1 over p. Derivative of square root of p, we know square root of p is just p raised 1/2, would be 1/2 multiplied by p raised negative 1/2. So the rate of change of temperature with respect to pressure is 34.96 over p plus 7.91, which is (3.955) times p raised negative 1/2. Now they would like to know the rate of change in the temperature when the pressure is 60 pounds per square inch. So all we have to do is plug in P equals 60 in the derivative. So dt over dP when P equals 60 is 34.96 divided by 60 plus 3.955 multiplied by 60 raised negative 1/2. Because we can make use of a calculator here. So 34.96 divided by 60 is 0.5827 plus 3.955 multiplied by 60 raised negative 0.5, 0.5099, and we get 1.093. So here is a problem that sort of uses the concept of finding extrema with a cost function. So what we have is a cost function that changes with respect to x, where x is the number of units. Now we want to know the average cost function. The average cost function is simply the cost function divided by x. So c bar of x could be equal to 100 over x plus 25 x over x minus 120 ln of x over x, which would reduce to 100 over x minus 120 ln of x over x. It is best to simplify this prior to proceeding. So if we pull 1 over x out, we would have 100 minus 120 ln of x. And if we pull a common term of 20 out, we have 20 over x equals 5 minus 6 ln of x. Now you could either use the product rule or you can use the quotient rule to find the derivative. I'm going to use the product rule. So now you may ask me, well, why is he finding the derivative? We are finding the derivative because we are trying to find the minimum average cost. So we know if we use the first derivative, then we could find that minimum. So to find the derivative, I am going to set u to be 20 over x and v as 5 minus 6 ln of x. U prime is negative 20 over x squared, power rule of differentiation. V prime, derivative of 5 is 0, so negative 6 times 1 over x. So using product rule, u is 20 over x, v prime is negative 6 over x, plus v, 5 minus 6 ln of x, multiplied by u prime, which is negative 20 over x squared. Twenty times negative 6 is negative 120. X times x is x squared. And over there we have 5 times negative 20 over x squared, which is negative 100 over x squared. And negative 6 times ln of x times negative 20 over x squared would be 120 over x squared multiplied by ln of x. We want to set this equal to 0 and solve for x to find the minimum. So we have negative 220 over x squared plus 120 over x squared ln of x equals 0, which would mean 120 over x squared ln of x would equal to 220 over x squared. The x squared would get cancelled, which would result in 6 ln of x equals 11. Which is a logarithmic equation. Ln would be equal to 11 over 6. Which would mean x is e raised 11 over 6, because how do we solve a logarithmic equation? We exponentiate on both sides. E raised ln of x would equal to e raised 11 over 6. Those two would go away, resulting in x is equal to e raised 11 over x. Which gives us an answer of 6.255. Let's say if that is true, we could verify this using the calculator to see if we made a mistake somewhere. And you've got to be careful here. We are trying to find the, or we're trying to graph the average cost function and not the cost function. So we want to plot c bar of x, which is 100 divided by x plus 25 minus 120 multiplied by ln of x over x. We are going to change the minimum and the maximum because x has to be greater than or equal to 1. So we'll do that, and it seems like we have x to be 6.255. And that is the graph that we are getting. So I'm going to use the calculator to find that minimum. So second trace, number 3, I'm going to go a little to the left of the minimum, a little to the right of the minimum. And the minimum is 6.2547, which is 6.255. And the value of y is the minimum average cost. So the minimum average cost is simply C bar evaluated at 6.255, and the calculator is telling us that that value is 5.814.